Good morning. Welcome to another SMAC seminar. Today we have the pleasure of having our Austrian colleagues, Paul Beck and Desmond Grossman, who will introduce the MESA library and the MESA code for computing models of stellar structure and evolution. This is going to be the first seminar, the most basic and introductory to the package. But we expect to have at least one or two more with more advanced uses. MESA is really a wonderful package that is not very much used at the IIC, we've learned, but is really used worldwide and is at the forefront of stellar evolution and structural models. And will give you, getting acquainted with it. It will allow you to, give you a lot of freedom and allow you to roll your own models whenever you need customized to your needs. So I think it's a very important package. Just quickly introduce our speakers. Both are from Austria. Paul Beckman graduated and got his master's in Vienna, and then his PhD in Belgium, Leuven, right? And now he's a Ramon and Cajal fellow here. Desmond is a PhD student here, and Akaisha, PhD student, and he's a graduated from Graz University in Austria. Please.
Thank you very much, Carlos, for the nice introduction. So, as Carlos mentioned already, this is a very basic introductory seminar on the stellar evolution code MESA. And I want to thanks to the collaborators, Paul, Savita, and those people who use MESA here. We will come to that in a minute. So, first of all, this is a hands-on seminar. So, we plan to install and run MESA code if you have a computer, if you're watching this in the recording or if you're watching it on the distance. I just send you a link over email and in the Zoom chat. I hope everyone got that. I can resend it in the Zoom chat again. And so the first part is to install MESA, we need some software basics, the so-called software development kit. This is a kit of Fortran compiler, other libraries and suites that is packed together that is made to run with MESA and other packages that are related to MESA. So in the link, you find a folder called MESA SDK, and I put 3 different versions in it. One is for Linux, one is for Mac with the old Intel processors, and the other one is for Mac with the newer Apple Silicon M1, M2, 3, 4, 5 processors. So you can also download it from the MESA SDK website if you Google MESA SDK. However, I found out yesterday this is extremely slowly. That's why I provided it with the cloud link. So I would now ask you, if you want to participate, to go to that link, download the one file that corresponds to your computer. I'm very sorry if you are a Windows user, it will not work. But for Linux and Mac, it will definitely work. So yes, so please download that file. On Mac, it's a little bit easier. You just need to click through the installation like you would install any other program. And in Linux, you need to unpack that file. And yeah, it's also not that complex. So I give you 1 or 2 minutes to do this, and let me know if you have questions. Yes? I sent it before. Yeah, give me a second. I just resend it. We will also keep this Zoom link later up. So we will put our slides there so you can do it yourself or you can show it to other people who might not have attended. So this is supposed to be kind of a permanent link where you can download the materials.
The other link, the official MESA
Yes.
There is fine decimal.
I put it as well in a document in this. I can show you in between. I put it here in a document where I have useful resources, and you see all the links that you need to download the latest version, the development version, the SDK, etc. So
That will sort of one can
yes,
copy.
exactly. So yes, that's this part. On Linux, you should not need any sudo privileges. On Mac, maybe. It depends on the Mac version. It's a bit tricky. For the MESA installation itself, you do not need any sudo privileges at all.
Ideally, this should become part of the suite of astronomical software that one can use on the IC network, maybe as a module. You mean part of setting? Yes. Exactly.
At the moment, this is installed by Fernando Perez Hernandez and by me on the Dolme cluster. That's the cluster of the SEBE group, because we are currently working with MESA. But yeah, the plan, as you said, would be to extend that to make it usable on anything. Because today we will try to run it on your laptops. That's usually how you start. But if you get productive, especially if you calculate grids, it will become more and more.
Can it be used with Slurm?
Yes, I'm using it with Slurm now for 4 years, 3.5 years, maybe something like that. And it can be easily used with Slurm together. It's even the recommended version if you run it on the cluster. Okay, everyone got the download? Please, if you have questions, anything, just ask.
And the latest version for different releases, or?
No, the software and development kit is the basics that you need for MESA to run. And the latest version is actually the MESA kit itself. So the software development kit is just like the Fortran compiler, different libraries, library Z, etc. You can all install them manually as well, if you wish. But it is recommended to use the software development kit because it is made to work with MESA itself. So the one is the prerequisite, and the MESA itself is then, sorry? Of the MESA itself, everything. Of the SDK, it depends. It's different suites. It's like the Fortran compiler that you need for Fortran code.
Compile anything already.
You need to compile it. We will come. Okay. Then I will proceed. So what you should know also, there's one zip file that's called MESA. It has around 2 gigabytes. It's also in the link. And you should download it. It should not take much longer than half a minute if you download it from the cloud. It is the latest version. You usually can download it from that link that I gave you, but we want to be faster. And unfortunately, the download servers in Zenodo are very slow. It took me 22 minutes to download it yesterday, so I downloaded it for you. And if you have done so, just move MESA, unpack the zip file to any location that you want on your computer. The downloads folder, the documents folder, the desktop, whatever you choose, whatever you want. And then basically we have 2 steps of installation. It's really basic in speaking of that. Yes, so please download the MESA file itself and unpack it to any location that you would like to do. And in the meanwhile, you can think what shell is your system using. So we will in a minute open the terminal of your choice. And we need to find the startup, the shell startup file. So basically in typical Linux, this would be bash rc. In up-to-date Mac, this would be ZSH rc. That's, in case you don't know, this is the file that basically your system reads when it starts up, and is setting different paths, different environment variables, so-called. And this is very crucial that we need to set, basically we need to set 3 of them, 3 to 4 of them. Don't worry, there's also a template. But first, please download the MESA zip file. I know this is now the boring part, but we need to have it to come to the fun part. Everyone who once has downloaded the file and unpacked it? I was really yesterday surprised how slow it was to download from Zenodo. Although I was in the high-speed Wi-Fi from the IAC, it took long. But from the cloud, it should get a bit faster.
I see there the variable OMP num-threads.
Yes.
So OpenMP is used for parallelization.
Yes. This is the parallelization that MESA supports, the OMP one. The other one, the name I always forget, it doesn't support. There's a second sort of parallelization, but the OMP one, it always supports. And for example, I play a lot with it and fine tune it when I use it on Google and on servers, because it's essential to, if you run it on one core, it will be very slow. But if you have, for example, 64 cores, you can run 64 MESAs in parallel. If you run it on 64 cores, it will be very fast, but you only can run one in parallel. So at the end, it's a trade-off. Here, I would just recommend to set it whatever number. It is sufficient if you set it to 2 or 4 for this purpose. If you want to do highly intense work, then you can set it up to whatever your computer supports. Okay, so please now open your startup shell file. So either, I guess it will be for Mac the ZSHRC or the bash rc, and it should have some paths, some settings. For example, if you have Conda installed, Conda automatically writes in those startup files or other ones. If you don't know what shell you're using, you can use echo $0, and then it will tell you what shell you're using. So yes, and I have provided you with this template in the clouds folder. You will see exactly this, and basically the only thing you need to do is take this template and adapt it to your paths. So the MESA dir should be where you unpack the MESA, the MESA installation. Can be anywhere you want. The OMP number of threads, you can leave 2, make 4 of it. Don't go higher now. That will be fine. And the MESA SDK, in Mac, it's usually automatically installed in the applications folder. So this will be fine for Mac. And the line source MESA SDK root, don't touch. This will be fine. And the last one also don't touch. This is just path inside the MESA directory. So the only two things you need to change is the MESA directory to your directory and the MESA SDK root where you installed the MESA SDK. In Linux, I'm not that sure. I think it is just the path where you put the MESA SDK basically. So, and in Mac, it's usually the applications part. So, yes, we are almost there with the installation.
The Fortran compiler that it comes with, is it GFortran?
Yes.
Is there any risk that if one has already an installation of GFortran, that the MESA install will, mess up things?
It could, but usually with this environmental paths, what I know, it will only install it like locally and make it only available for MESA to use. So it will install, that's the reason why it has its own applications path and own MESA SDK path, that it doesn't mess up. I have heard of things where it messed up. So, but I think recently in the last 2 or 3 years, they separated like very nicely. And that's also one reason to use the SDK, because it comes as one package. If it messes up anything, I can also give you the instructions to deinstall MESA SDK again, and it should be fine. It should not uninstall. I think the maximum thing is that it might override the path to GFortran. But yeah, so, but this currently, those use the latest version of GFortran, to my knowledge.
And do you have an approximate idea of how much space is needed for the whole install? Are we talking gigabytes or tens of gigabytes?
I think the SDK, maybe a few hundred megabytes. It's not a lot for the SDK. For the MESA itself, it's zipped, it's 2 gigabytes, and I think unzipped it's around 10 to 12 gigabytes. What really eats into your hard disk space is the equation of state tables, because there's a huge tabularized equation of state tables, and for all different scenarios. So this is really what costs the space. So it should be, I would say, 12 gigabytes, more or less. I think I didn't check recently. I checked a few years ago, and there was around 10-ish. I think they recommend you to have 20 gigabytes free, but usually it eats less. So 20 is like, to be very sure. Okay, has everyone set up environmental variables as they like? So what you need to do now is to go to save the file, and then you need to source your startup file. So just type source and then the path to your ZSH-RC or to your bash-RC file. And it should give you no output at all. If it gives you an error, you maybe have a typo in the path. If it doesn't give you an error, this is usually fine. And then this is the last step of the installation. And after this, I will hand over to Paul.
Desmond.
Yes.
So I understand then that it's compiled from source, right?
Yes. And it's a very interesting concept, because before you run, we will see we need to compile it with ./mk. And then it will create a binary, I think it's called star.bin, that uses, that has everything included to run it at the end. And the nice thing is that usually you should get the same results because you compile it on your machine, so it will be adapted. But the input files, so if you give me a MESA directory, with your input files and we use the same MESA version, I should get exactly the same output on my computer as on yours. Different versions is a different topic. This is a bit difficult, but yeah.
Is there some like verification checks, files that will verify that actually your version, your compiled version gives the same on a test?
It will shout to you. If you try to compile it and there's something missing, it will violently shout and tell you you did something wrong. Okay. So if you sourced your file, your startup file, please change into the MESA directory. This will be the first check if you set it correctly. So just cd into the MESA_dir. If you arrive in the MESA dir, it will tell you you did something right. And if not, go back to your startup file, look if your MESA part is set correctly. And if you were successful with this, just type /install. And this should do the magic, hopefully. I tested it yesterday with this version. It worked, so. If you get an error, let me know. I can help you. It will now run 5 to 10 minutes approximately. And in the meanwhile, I will hand over to Paul to give you some basic introduction on what MESA is actually doing and how this relates to the stellar evolution structure. So just let me know in the meantime if you need any support. Okay.
Okay. Thank you, Desmond, for taking care of all the technical stuff. That's always the bit annoying part until it compiles. And well, now I have the pleasure of compressing a full lecture in 3 slides, which is stellar structure and evolution. And what you see here is a pretty picture summarizing what a star is and how it evolves. A star is defined as a self-gravitating, self-luminous quantity, which is in equilibrium. But depending on the mass, the path the evolution will take is very different. And this is shown up here. On the vertical, you have the mass going from very low mass stars at the bottom to the very high mass stars on top. And it's a basic principle of stellar evolution that with the mass, the speed and the evolution are depending. And this is what you see on the horizontal. That's the time the star is taking and evolving. And you see several subsequent stages of the evolution depicted. And of course, if you take a star like the Sun with 1 solar mass, it will spend 10 gigayears on the main sequence and then evolve off into a red giant and further into a planetary phase, into a white dwarf. If you make it less massive, it will take much longer and might not even have seen the red giant phase at the end of the universe. If you make it more massive, it will take much shorter for that evolution. This is just what we see from the outside, but those changes go along a lot with stellar changes in the deep interior in the stellar structure. And this is what is shown here. For example, on the main sequence, you see on the left so-called Kippenhahn diagram, which shows the structure, which compares the structure of different masses shown on the horizontal horizontal axis versus the integrated mass. And where you see the clouds, this means those are convective regions. And you can see that this change from about 0.3 to 50 solar masses is significant inside just the main sequence star. Where this comes from is basically how we describe, well, how do we describe stars? And this is reflected in the structure. We describe a star with a set of 4 differential equations, which are known as the stellar structure equations, which describe the radius, the pressure gradient, the temperature gradient, and the luminosity. However, what looks pretty simple up there is a full set of equations and a lot of parameterized effects inside that we don't even know about, or we have to guess or parameterize. But those are the 4 basic gradients that describe the stellar structure. Now, how is it done in MESA? MESA, in stellar structure and evolution, we are describing a star as a one-dimensional object, which has the coordinates of the integrated radius or mass. And you see, which we call the mass or radius coordinate, which is 0 at the core and 1 at the surface. So we describe it as fraction of the mass or radius coordinate. And well, this is a one-dimensional model, because if you take this string and you project over a sphere, you get a star. And the joke goes, what's the difference between a 1 and a 3-dimensional model? Well, the 3-dimensional model is 1 in 3 dimensions. With this, we can describe the star. And what you see in the diagram here is how MESA and all other evolutionary codes are describing the deep interior. They are chopping the star in the stellar structure in several hundred layers, and they are not equidistantly sampled. This is how a stellar model of the sun is looking, and it's using about 800 layers, and each cross is marking the border of such a layer in a mass and radius coordinate. And you see that in the deep interior, you have a very sparse sampling, and most of the 800 layers are at the tip of the path, basically where we have the convective envelope. So the distribution of those shells is done dynamically based on the variation controls, which means how big can a step size between 2 layers be. And this is done on either a manual input, where you set an upper limit, or it's checking the parameters inside the model or inside the layer, and does not allow for changes bigger than a threshold. With this, and then it's calculating the interaction between layers like radiative transport or angular momentum. Most of it is done as a diffusive process. Now, the way how the layers are sampled will have great impact on your resolution and on the results of your model. The finer you calculate, the finer you will sample the structural changes from one layer to the other. On the other hand, it will also increase your computation time per model. And for each layer, those parameters that are calculated are written into what is called the profile. You can set the step size on how many models you want to output such a model. And you can define, as Desmond will detail later, what parameters or how many parameters you want to have in there. Because those are the ones you will use later on in your, when you plot, when you calculate. This is what you will use. So this is one stellar structural model currently for the sun. Of course, we want to change, or we want to check how those models are changing from one to the other time step. And we always say that the mass is setting the pace, but the change in chemical composition and energy production in the central regions of the star are driving that change. And this is modeled from one model to the other. And also here, the time steps are driven by either the manual input or the quality control that limits the change to a certain step size. For example, you can say the increase in luminosity should not be bigger than a fractional value of, or the change in radius should not be bigger than a fractional radius. On the other hand, you can also put a lower limit saying you do not want the time step to be shorter than X years. Sometimes you have to limit it to 10 years to avoid that the model undergoes shorter and shorter time steps and will never finish. So what you see here is an evolutionary track of the sun from on the pre-main sequence into the main sequence, and then the red giant phases into the white dwarf. And those parameters are written out in a history file, and you can say how many steps you want to have written out, or which models you want to have written out. And this is then what is called the history file. And again, the finer you allow your model to calculate, the better the structure will be, because on the red giant branch in particular, the resolution and step size will have an impact on how the model is evolving. Basically, one thing about stellar evolution, we have a lot of assumptions in there, and as longer as the model goes, the longer we accumulate the effect of the assumptions. And that's why the red giant phase will be basically a mirror of the misconceptions on the main sequence. So this is how we can test also stellar models. With this, I hand back to Desmond for the details.
Thank you, Paul, very much for giving the basics and really the essentials of what is happening under the hood in MESA. So let's continue one more slide with technicalities. If you have any problems, and this is especially for those people watching recordings, doing it later on, etc., first look at your shell startup file. Did you set the paths correctly? Is the MESA SDK installed, unzipped? Common error on Mac is so-called the library Z not found. I had this yesterday as well. So the solution is just to put this line into the MESA SDK of it. This is some interoperability problem of MESA and Apple Silicon workings under the hood, but it should not, if you add this, it should work fine again. And if anything doesn't help, just try again. Go to the MESA directory, first do a clean, /clean. This will like erase everything that was produced during the compile, and then do a /install. Just at the end of the startup of the shell startup file, where we put the other paths. This was not necessary until last year, and suddenly something broke compatibility, and then it was a bit messed up. Okay, so if this is done, I can give you now a little bit of an overview what MESA is less under the hood, but in general. So what does MESA actually stand for? So MESA is Modules for Experiments in Stellar Astrophysics. We will come why modules in a minute. And after AstroPy, and I checked this, it's the most widely used open source tool in the astrophysics community, which is quite a statement. MESA has over 14 years of development. It started to my knowledge, in late 2010, beginning of 2011. And it all started with this guy in the middle, Bill Paxton, and to his left, Lars Bilsten at the University of California in Santa Barbara in 2010. And Bill Paxton is actually a computer scientist. Lars Bilsten is an astrophysicist. And Bill Paxton was the co-founder of a small company we know today as Adobe Incorporations, and retired early. and then made MESA to one of his projects together with Lars Bilsten. And that's how the code came to be. As I mentioned, it's written in Fortran, and it's open source and community driven. Everyone can use it, but not only use it, but also contribute to it. And many, many things MESA has today in 2025 is actually was coming from community contributions. So if you compare it to what was MESA in 2010, you would not recognize it again in the positive sense, because so much more things were added, so much more capabilities were added. So to my understanding, MESA, it was not written completely from zero, from blank. It was based on a very small non-open source code from the late 90s, I think, and then extended and modernized. But the problem is Fortran is extremely efficient. And I mean, I'm not the biggest fan of Fortran itself, but it runs very, very efficiently, and that's what you want with Stellar evolution codes to have it. And yes, and it's a bit of like at the end, the trade-off, of course, in, I don't know, C, it would run much faster, but it's a much higher level programming language, and Fortran is much easier to get used to manipulate, as we will see in a minute. So who is MESA? MESA is all those people. Those are the current developers of MESA. Meredith Joyce, Warwick Ball, Rich Townsend, Bill Wolf, Jared Goldberg, Philip Motzk, etc. And you will see all those. I didn't find a more up-to-date map, but those were the community of MESA that were actively participating in MESA and contributing in the year 2021. And you see this one little dot in the Atlantic Ocean, and this is actually us. Savita Mathur, back then Fernando Perez Hernandez, who has retired recently, Paul Beck, and myself, that were actively using MESA and subscribed to the MESA users list, for example. And it is a very nice example to see how widely it is used in the community, basically everywhere. So I mentioned MESA modules. Why modules? So usually when people talk about MESA, they mean MESA star, the core module of MESA that is calculating a stellar evolution of one star to whatever liking, whatever input you give. However, there's also a binary module. Surprise, it will calculate the stellar evolution of a binary system and take into account also orbital factors. And one level below those two modules, there are different modules for atmospheres. You can make many, many settings regarding your stellar atmosphere. Opacities, a kappa module, you can make settings regarding the opacities. Nuclear reaction network, you can manipulate basically any nuclear reaction you can imagine you find in a star, you can manipulate. Synthetic photometry, this was just added recently, like less than a year ago. So you can make MESA output all of sorts of synthetic colors that you might need for comparison with mission data, with other synthetic models, etc. Another important point of MESA, and basically the reason why we do MESA here in the SEBE group, is astroseismology. So it contains 3 different tools for astroseismology. The Astero kit, which is now a bit outdated and I think not further developed. The Gyre kit, which is a standalone software in itself, but also included into MESA, which is a stellar oscillation code. And it can directly, smoothly work either in post-production of MESA or in parallel to MESA with the output data. And Adipose, which is another stellar oscillation code as well. So MESA is not only the star module, it's the composite of all those modules. That's what's important. And MESA is not only a composite of all those models, but it's embedded in an ecosystem of various suites and tools. So you see here MESA as a big gear You also see like nuclear reaction codes, you see spectral codes, you see chemistry codes, you see 3D hydrosimulation codes, you see the pulsation codes I mentioned. All those things work hand in hand. So you can use MESA output or even give it as an input with various different things, like the mist isochrones. Maybe some people have worked with that here already, which are just isochrones that were produced from MESA, and it's basically pre-calculated MESA models that were interpolated at the end. So this is all a huge ecosystem where MESA is a central part, but by far not the only part of it all. So what are the capabilities of MESA? So MESA runs almost all stars across the HRD. Brown dwarfs, M dwarfs, solar-like stars, red giant stars, OB stars, white dwarfs, even planets you can run. You can even do supernova with it, although I'm a little bit skeptical of it, but technically you can do it. It is originally conceived, optimized for massive stars, but currently, to my knowledge, it's used more in solar type, like solar mass stars in that range. And that's also what we use it here for solar-like stars and red giant stars. You can use it for binary evolution, as I mentioned with the binary package. You can add mass gain, mass loss, mixing length theory, different atmospheric effects, opacities, as I mentioned. So this list could go on for at least 3 more slides, but I wanted to summarize the most important things here. So it has very huge capabilities. If you say, okay, I want to use MESA for science, how do I start? I have it installed, I run the tutorial that we'll do later, but how will I start? The start is the starting point is the test suites. Those test suites serve 2 purposes. One is to test a new release of MESA that arrives every year-ish, more or less, sometimes every half year. And the other thing is, it is a base for the science that people do with MESA. You see here an example of, I think it's not everyone, I could not fit all of them on one slide, but it's a good example of different test suites. You see make planets, make metals, high metallicity, 1 solar mass 3 main sequence to white dwarf, etc., etc. So you see many of them. You will all find them in the test suites subdirectory of your MESA installation and in the documentation. And you can basically look if you find any of them suitable for your science, you can take this as a starting point. However, caution, the test suites are made to run fast because they are made to test MESA, and you don't want to wait 7 days for MESA to be tested. You want to do this in a night. So they usually run with low resolution. See the variation controls that Paul explained very nicely. Both low resolution in the sense of spatial resolution, but also temporal resolution. So this might not be fit your science, because you might want to analyze, like I'm doing, the red giant branch, and then you need a higher resolution. This is not what is usually given in the test suite. So you need to adjust those variation controls, delta T, delta L, etc. Second caution, all settings in MESA have defaults. So even if you do not give, for example, an initial mass of the star, MESA will run, because it will assume the initial mass of the star is 1 solar mass. And then you will be surprised why it runs when you didn't give an initial mass. Same for metallicity and all the other settings. So all the settings have defaults. And you can see those defaults here very nicely. You see, for example, here, initial mass, 1, in the units of solar masses. Initial Z, initial Y, etc., etc. All those are defaults. They are very well documented on the webpage, so you can all scroll through them. But be aware, there are the defaults given. And take a special care of units, because some of the settings there are 2 or 3 settings for one property, but in different units. You can give the star per default the stellar mass in solar masses, but you can also give it in grams. And you don't want to set the star to 1 gram and then be surprised that the star doesn't actually evolve. So take care of that. It is very well documented. You can either look it on the web page or in the defaults directory that I linked, and you will see it is very nicely commented. It will tell you what it is, how it works. So just that you know. Okay, this was the background for MESA. And now we come to running our first model. Nicely enough of the MESA developers, they have included a tutorial, which is exactly basically meant for what we are doing right now. And so what I would ask you, if your MESA installation was successful, what I would ask you to do is to go to any directory of your liking where you want to work, and then just copy this tutorial in the MESA directory /stars/work to, I called it tutorial because that's the usual convention. And yes, so that we have it. If you then go with whatever program you use, either the terminal or the Finder, the Explorer, into that directory, you will see several different files. And those are the core of MESA input. They're called inlists, which comes from Fortran, because that's how they are called in the Fortran language. And you will have a file that is just called inlist. This is a very boring file because nothing happens here. The only thing that happens here is for every category, those inlists have category. I think I could give my own lecture what's the difference between those categories. I think it's not essential for you to know. The documentation will tell you in which of the categories which setting will go. There's a star job, equation of state, kappa, controls, and PG star, which will come later too. And here it just tells MESA, okay, here you won't find anything. Go to the other inlist called inlist_project. Okay, so we go to inlist_project. Here it gets more interesting because this is actually filled with with information. And this is actually the essential data where it will tell you what do you need. For example, in the star job category, you can tell MESA it should save the final model when it terminates. So you set save model when terminate as true when you want it. And then you can set the save model file name. In the control section, you can set the quantities where you want with which you want to start your model with, for example. So you can make all those settings in those inlists. And now I would like to ask you to look into, yes, so I said that already. So look into the inlist project. What is the current initial mass of the model in this tutorial? Anyone opened it? You can even open it when the installation failed, because the file will be there and unpacked. So if we look closer, the initial mass is given as 15 solar masses, and it has given a stopping criterion. I put this screenshot here, but it did not appear. I'm sorry. And as a stopping criterion, it is set that when the central hydrogen falls below 10 to the -3, it will stop the model. This is also essential. You need to set a stopping criterion for MESA. Again, there is a default value, but that might not fit your science. However, even if you deactivate the default value and do not do a stopping criterion, your model will evolve until the end of the age of the universe, or until your computer runs out of battery. And this is not probably what you aim to, so you need to set this. So for this task, if you want, we can change the initial mass to 20 solar masses. This will drive up a little bit the speed of the evolution of the star. And you can set the initial metallicity to 0.01. This is just a hands exercise to do it. You can open the inlists in any text editor you like, in Nano, in Vim, text edit, whatever you want. It's just a simple text file. So you can manipulate as you're liking. If we go more advanced, Paul and I did that some years ago. You can even let those inlist files be written with Python, for example, or any scripting language of your choice. So this is really very flexible how you do this. But now it's manually done. So if you changed it or not changed it, save the files. And now basically the only thing is left is we need to compile it, which is done in MESA with ./mk. And then it will take 5 to 10 seconds and it will spit out a lot of code that is very gibberish. And at the end, it will hopefully not give you an error. And just, it won't even say it compiled, but it will just jump back to the terminal and it will be fine. And then at the end, and we can do this live here. I killed the server. I just need to. So if I do it, you see it, right? Make it a little bit bigger, then it's easier. So we go here, we compile it. It's fine. It gives you a warning sometimes, but a warning is okay. An error is not okay. Then we can go and say .rn. And then the magic will happen. So what's MESA now doing? In the first steps, it will try to find a pre-mean sequence model that is actually fulfilling the equations of state. And when it has done this, it will show a graphic surface, the so-called PG star plot, which we'll see in a minute. And all the quantities outputs you see here, they are not necessary, but they, by default, they are on. You can also set them off. When I use it on a server, I set them off usually. And it usually gives you all the stellar quantities that are related to this model and how they are changing over time. And now you will see here a Hertzsprung-Russell diagram of the star evolving right here. And you see the star is here and it will evolve, if I'm not mistaken, now over here. First down, then up, go here. And this is called a T-rho profile, so a density versus temperature, which will basically give an idea in the colored versions which zones you have in the stars and which zones are dominating, mixing, convection, etc. Which is quite nice. And the dotted lines will show you in a second the hydrogen burning will start now. And if we reach then later the helium burning will start. And this is a model that runs very, very fast. It should be done in now. So this is just made for demonstration. Don't get pampered by this. Usually my MESA models run for days. So this is the contrast, but to show this is pretty enough. So yeah, I showed you the visual output. And then I would like to emphasize again the post-production, the MESA output. Paul already explained it very nicely. You find all the output files in the logs subdirectory that is freshly created. So wherever you work, it will create a log subdirectory, and there it will have the history file, which is the stellar properties over the stellar evolution. And this is one file per run. And so see the slide 8 from Paul. And then there's the profile file, which shows the stellar structure at a given point of evolution. And there are usually several profile files per one run. I think in this one, there are 4 or 5 profile files, which is also a setting you can make. You can tell MESA, please put a profile file out at every time step, every second time step, every 10th time step, whatever you prefer. The problem is if you have a long stellar evolution, it will be a lot of profile files, which eat a lot of space. But if you need it for your science, this is what you need for your science. And both of them have a standardized structure. So the history data file looks something like that. So you have the stellar age, for example, given here, and every row is one model step. So you see the star starts at the ages of hours and then develops up to, this is given in the unit of years, then it develops up to tens of years, thousands of years, 100,000 of years until it stops. And same for mass. This stays constant because we don't have set mass loss. If you have set mass loss, for example, this will not remain constant, of course. But how does MESA know what to put in this output file? You can set it. This is called history columns list. And this is the so-called default file. And if you open this history columns list, which is in your MESA directory, you can set almost any quantity of your liking. For example, here we output the central hydrogen, helium-4, carbon-12, oxygen-16. You can set almost every chemical abundances here that of your liking. And also the standard ones that are active is stellar mass, stellar age, radius, etc. But you can really set a lot of quantities in this default file. And then you can choose to output more, output less, depending on what your science case is. And this is already the last step. Now you have this output. What do you do with it? I mean, you can look at the table and hope you will have any knowledge from it, but this is not how we do it. So what you can do is you can go to your favorite Python environment. Doesn't really matter which one it is. And then there are 2 options. Option 1 that I personally recommend is the so-called MESA reader, which is a library in Python, a very lightweight library in Python that you can just pip install with it. Or the second option is the pure NumPy, which uses the NP gen from text, which also works very, very nicely. And you see here an example script. I've given you this script for the MESA reader and the other script for the NP gen from text in the cloud file. And this one you can use to produce, for example, here an Hertzsprung-Russell diagram. So you just put in your directory where your history file is located. Then you do a matplotlib plot, put the labels in, and it works very nicely. If you have done this, I will demonstrate it here. I think I have it open in the Jupyter notebook, yes. So for example, if we do this, we should get something very, very rudimentary. That is the Hertzsprung-Russell diagram of this star. This will probably not be suitable for your science case because this is just a tutorial, but you can do it with any output, with any history file. Why I said I would recommend MESA Reader. MESA Reader acknowledges there are some differences depending on which MESA versions you use. And the MESA Reader knows these differences and adapts to what file. If you use the NumPy only version, it works as well, but you might need to fiddle a bit around. At the end, both work generally very fine. And you can access, as you see here, you can access all the quantities. For example, log luminosity, log temperature. central hydrogen, whatever. You can here I plotted didn't put labels here, but here I plotted just to see the stellar age over the log of the radius, for example. So you see this generally works. And then you can, of course, use these quantities to make calculations, put it into formulas, and further use it for actual science output. For example, what I'm doing currently is I calculate a grid of many, many models from red giant stars, and then I take the history file, I take the profile files, which I put into Jira, calculate the stellar oscillations from it, and then put it all together. And from this one big pandas data frame where I put it in, I do a chi-square minimization to find the best fitting models to the observables. For example, this is just one of many, many, many examples that you can do. And with this, I would like to leave you with some resources. They are all linked as well in the cloud directory. You don't need to type the links. So the latest version you can always download in the Zenodo. If you want to look into the development, or if you're interested what capabilities are added, you can look into the GitHub. The SDK is separate from which Townsend provided. And also the code itself, you can look into the test suites. They have very short description, all of them, what they are actually doing. And also the defaults that I mentioned, you will find them in the defaults directory of the code. And the whole documentation is given into the docs MESA star. And just half a year ago, they got a very nice new shiny website where you see this is one of the plots that runs concurrently. And here you see all the resources that you can think. Here's MESA Reader. Here's MESA Marketplace, which is basically there are scripts from other people that you might find useful because they might match your science case. There's another community, the SDK, MESA itself, etc. Here also, if you want to go deeper into it, the MESA summer schools and materials to the MESA summer schools, which have now happened for, I think, over 12 or 13 years every year in different places on this planet. And the documentation is also given very nicely here. For example, the defaults I showed you before. Also, installing MESA is here described very nicely. The modules, etc., etc. You can get a quick start. So this really, really well documented. This wasn't always the case when I started with it. I think half of the documentation did not exist, but in general, this is very, very well documented, and the community is also very nice. There is a MESA users list, so if you really start using MESA, you can subscribe to the users list. I showed you, I think I showed you here before. Yeah, you can subscribe here to the MESA's users list, and here you can sign up for the mailing list. Even if you're just starting to use MESA and you want to be informed about new releases, the summer schools, etc. But you can also, if you're using it and if you have troubles, you can also mail to this users list, and some of the developers or more advanced people will answer. I've also answered to MESA posts, to the basic ones, for example. So this is a really nice open community. Everyone can use it, everyone can participate. And with this, I want to say thank you.
Thank you so much for this wonderful introduction. Now, if there is any comments or questions that may come up. Let's see if there is anything online. Okay, no, I don't think so. If anyone online wants to ask a question, we're not that many. Can just open the mic and directly ask, or
You can scroll down.
oh yeah, this is at the top, right? Okay, yeah, there is. Does MESA include anything for making synthetic spectra? Might.
I don't know if it includes it directly, but if I'm not mistaken, it works like you can plug the MESA output, the profile files, into at least some synthetic spectra codes. I need to look it up, but I know that people were doing that. I don't know if you can do it directly. I don't think so, but it's definitely compatible, the output of MESA, with a synthetic spectral code.
Yeah. I was curious to see that you compile actually every model you were going to compute.
Yeah.
There is a compilation there. I guess that's reflecting this module structure
Yes.
that you mentioned, right? You're actually producing a code for a problem.
Yeah.
And could you also go back to this slide at the very end where you're showing the HR diagram for the 20 solar mass model?
This one?
Yeah, or the plot that you produce with Python
Yes.
at the very end. Yeah, this one. Could you briefly, because I got a bit lost. So you stop the model at the end of the main sequence?
No, the stopping criteria I didn't change in the tutorial. I think it was set to a certain fraction of central hydrogen. I don't know the amount, but we saw in the plot before that it stopped before helium burning, so before hydrogen depletion. I don't know exactly. I think it was 10 to the -2. It was just made basically to run very fast. It's not nice.
What are we seeing here? Because we normally are used to see stars, landing on the main sequence and then going off.
Yeah.
But here you see the pre-main sequence
development, yeah.
and then goes to the left.
Yes. So what is important in MESA is always, and this is also a philosophical discussion in the MESA community. Do you need to calculate a pre-main sequence model for every model that you do? I mean, if you're interested in pre-main sequence stars, you obviously need to do it. But people that work on later stage developments like red giants or other stars on the later stage, MESA has the capability that you throw a pre-main sequence model at it and say, please use this pre-main sequence model and then continue modeling it from the point the pre-main sequence model stops. And so this is the one possibility. The other possibility is basically to let it do the pre-main sequence calculation itself, which of course takes more time. Not really if you calculate one model, but if you calculate 1,000 models or 5,000 models, you calculate the pre-main sequence for 5,000 times. And then there's the debate of how much does it change if you just provide a grid of pre-main sequence models and say, okay, then develop from the pre-main sequence onwards. And here it goes through the pre-main sequence. I mean, we can look at the code itself. Nano InList project. Yes, so it stops here. The stopping criteria is given as the central lower limit of hydrogen, 10 to the -3. So 0.1%. And the second stopping criteria that is given is it stops when the star is near the the 0H main sequence. So it's just basically developing up to that. And this is also an important feature of MESA. You can give multiple stopping criteria. You can say you give the stopping criteria that you want the model to stop. But if for any case it doesn't reach this stopping criteria because the evolution is maybe a bit different than you expected, you can put another stopping criteria into it. So this is one of you can put 5 stopping criteria. I would not recommend to put more than 2, because at the end you might not know which stopping criteria actually stop the model, and then you might get into confusion. But in this case, I guess the model stopped near the zero age main sequence. That's why the HRD looks so uncommon. But you could develop it further on to whatever age you like or whatever you want. This is just to show as a tutorial.
Yeah. Just to comment on the previous question, why not Python or C++? MESA is very modular, and you basically can change whatever you want in the code. You can, if you have derived a new code for agricultural transport and you want to test it, you can implement it yourself. And this is and there's several ways, and this is why it's all in Fortran as a compromise between high-level programming language and efficiency. So it's a lot of things can be added in all of it.
Maybe trying not to go maybe over a lot of time, but another question that a lot of viewers may wonder, what about if one targets to compute isochron, say, for example, right? That would require a whole collection of models. Are there tools in MESA aim to finally, in the end, build or facilitate building an isochron?
I mean, this is basically was the target of the MIST project, and the MIST isochrons are now relatively old. They were built on I think on the 2015, 2016 version of MESA, something like that. They want to build, what I've heard from the community, a new set of isochrons with current physics, current MESA version. There is a tool that is provided by the MIST community to make it easier to develop the isochrons. However, you still need to calculate your evolutionary tracks, because MESA is simply an evolutionary model. You need to go from the beginning to whatever endpoint you set, that you can then at the end make an isochron out of it. But the MIST community will provide updated isochrons maybe end of this year, not next year. So they are actually very useful. And often what I've also heard is that MESA and MIST are confused with each other, because those are two different things of the same metal, I would say. They both come from the MESA stellar evolution models, but the MIST is one static set of isochrons that is amazing when you want to see I just want to go approximately there and I want to see how the stellar evolution track is. MIST is beautiful. But if I want to do my customary modeling, MIST is not in that sense helpful, because it's not made for it. It's not the purpose of it. That's the purpose of MESA. And so, yeah, so for isochrons, I would recommend MIST and hopefully the updated versions, because calculating isochrons from MESA itself on a high cadence will take you time.
All right. Any further questions or comments here? Let's check online if there is any further one. Oh yeah, there's one. The Wimble. Does MESA has astroseismology data like the astroseismology parameters for the evolution stage?
Yes, excellent question. Good that you ask an astroseismologist about it. The core part is that we have heard that MESA outputs those profile files, which contain the stellar structure. And alongside those profile files, you can output basically a similar file that can be different format, for example, in the format of Gyre, but also in other formats of other stellar evolutionary codes that can be directly used by almost any pulsation code, astroseismology code of your liking. Gyre, Adipose, what other codes we have? RSP, which is also a pulsation code. So you can directly put that in. And with Gyre, which is the most integrated one, you can even make it run in parallel. So you say you evolve one evolutionary track, and you can say as soon as one profile is done, it starts a parallel process with Gyre calculating the actually pulsations and outputting the pulsation frequency. So you just basically need to change one setting that it outputs these special profile files, and then you can use it directly in any astroseismology code of your like.
super useful. But regarding this question, I mean, to know whether a star has reached or is in the red clump stage, wouldn't just the code let you know because it's burning helium at the core and it's on the right luminosity and temperature? Yes, you probably don't need this small.
If you only
need it
look
with
at
a
the
real star in the simulation, but
For real star, we don't know it, it's burning.
right.
But
here you know.
there's a lot of magic going on that luckily you want.
I mean, for example, what you can do is that the delta pi, this quantity that you can use with other quantities to separate the red clump from RGB stars, you can calculate from the oscillation modes when you put it into gyro, for example, and then you get a delta pi quantity out of it, and then you can see on your chart, is this rather a red clump star or an RGB star? But of course, for the model itself, you know it by looking at the evolution, but for the observed stars, you don't.
All right, let's stop here. It will be, I think, super useful for the next, for the follow-up seminars, if the viewers give input to me or Desmond and Paul about, what particular utilities of these other additional codes and utilities around MESA would be most interesting for them, so that we can customize those next talks. Thanks again, Desmond. Thanks again, Paul.